All right, guys. Can you guys hear my audio?
Yes.
All right. Let me adjust it just a little bit. Okay. So I want to talk about, last time we were together, we talked about capacitors. I want to talk about capacitor charging and discharging circuits today. And at the end of the lecture last time, we talked about 3 important times. I want to talk about those times and go into some details. Before we get into the details of it, let me show you what a charging circuit looks like. A simple RC charging circuit. So I have a voltage source. I got a switch. A resistor, and a capacitor. So here's the R, and there's the C. So they call this a RC circuit. Here's my switch, and here's my voltage source, my total voltage. Now, let's look at what happens when we take the product of R and C. So I'm going to take R times C. And the question is, when I do that, what kind of physical quantity do we get? So see if you can follow what I'm about to do. We know from Ohm's law that R equals V over I. And we know from the previous discussion that C, capacitance, is Q on V. So I'm going to substitute for R, V on I, and I'm going to substitute for C, Q on V. And you can see what's going to happen here. My V's are going to cancel out. And I end up with Q divided by I. Or if I write it the other way, I end up with Q divided by I. Now you got to go back to the second week of class when we talked about current. Remember current, I'll put it over here. Remember current is defined as charge per unit time. So written as an equation, current is Q on T. So I can substitute for this current value, the value Q on T, and now you see exactly what's going to happen, and you see what makes this circuit very, very, very interesting. What happens is I get Q times T on Q. The Q's cancel out. So the answer to this is the product of RC equals time. Time. This is a very, very, very important relationship. The product of RC gives me time in seconds. Now, this product of RC, put it over here. This product of RC is so important that they give it a name. They call it a time constant. A time constant. And they use the Greek letter tau to represent that. Like pi, 3.14.
Sir, excuse me.
Yes?
I don't see the whiteboard.
You can't see the whiteboard?
Yep.
Can
The light.
He's talking
The
about
light
the
disturbance.
section where it says time constant. You can't see that.
Oh, right here?
Yep.
Yeah,
Is there glare there?
yeah, we can't really see it.
Is it?
We can see the time, but we can't see the constant.
Wait a minute. Is the camera too low?
No,
Hold on.
it's the light. The light.
Oh, it's the light. Hold on a second. Is it better now? Let me check something. Hold on a second. I don't know what to do with this lighting down here. Give me a second to check it out. I'm gonna log in on another computer and see if I can see what you guys are seeing. This work on this time. Okay, guys, let me know if you can see this board still. Can you still see the board, or is it too dark?
Now we can see everything.
Okay, it's not too dark?
Nope, everything's fine. For
Okay.
me at least.
All right, what about the rest of you?
For me
Anybody
now,
else?
it's okay.
I can see
Works for
just
me.
fine.
Okay, all right. So we're gonna roll with this. It's a little dark, as long as you guys can see. I went up and logged on another computer to see how it looked, but we'll go with this. If it's too dark, let me know. I'll turn the light back on. Now I got a little shadow over here, so hopefully you can see that. Okay, so let me go back through what I said before. I wanted to look at the product of R times C, and through my calculations, you can see that we ended up with time. So what I said was this product of RC is so important that they give it a name they call a time constant. And the way they denote a time constant is with this Greek letter tau. So tau equals RC, a time constant. So for example, if you had a resistor value of 10 megohms and a capacitor value of 1 microfarad, then you could get the time constant 10. Now remember, megohms is 10 to the 6 ohms, and microfarad would be 1 times 10 to the minus 6 farads. And you can see what's going to happen. Basically, my units will cancel. Get rid of this and this, multiply this, I get 10, but the units are seconds. So for this problem, one time constant is 10 seconds. Now, I'm going to explain the significance of this time constant thing in just a second, but just remember that when I take the product of RC, what I get is time, T-I-M-E, time. So here's an RC circuit. I want to look at the behavior of this circuit when I close the switch. When I close the switch, the second I close the switch, we're gonna define the time that I close the switch. The instance I close the switch, I'm gonna call that either t sub 0 or t equals 0. And again, this is the instance switch is closed. I mentioned to you last time and today that we're going to look at 3 important times. This is one of those times, t equals 0. So t equals 0 is defined as the instance the switch is closed. Let's look at what happens when I close the switch. Now you got to kind of think about it like this. When I close the switch, current is now going to flow into the capacitor. Hold on, guys. Yep. Okay, sorry about that, guys. That's the disadvantage of working at home. People can just interrupt you. All right, so we'll get through this. So let me go back to what I said before. At t equals 0, the instant I close the switch, current flows in through the resistor into the capacitor. Now, that resistor actually acts kind of like a check valve. This should make sense to you. The bigger the resistance, the lower the current that can go in to charge the capacitor. If I want a lot of current to go into the capacitor, I have a lower value resistor. So basically, I can control the speed at which that capacitor charges up, and that's where that time constant comes into play. Actually, tau equals RC. By choosing the proper size R and C, I have total control over how long it takes that capacitor to charge up. But again, I'll get to that in a second. Let's look at what happens, though, as the capacitor charges. A couple things. Charge, in this case, equals voltage. And what I mean is the more charge the capacitor has across its plates, the more voltage. At t equals 0, the instant I close the switch, no current has flown into the capacitor. The capacitor hasn't charged up yet. It takes time for the capacitor to charge up. So basically, no charge means no voltage. And let me put a voltage here. Let's just say this is 10 volts. We got a 10 volt source here. At t equals 0, no charge has flown into the capacitor yet. Charge equals voltage. And since no charge is in the capacitor, there's no voltage across the capacitor, that means that entire 10 volts is across the resistor. Kirchhoff's voltage law has to apply here. So what happens, I have 10 volts across the resistor, which means 0 volts is across the capacitor. 10 plus 0 is the 10 volts applied from my voltage source. But then the clock starts to tick, the capacitor starts to charge up. Let's say the capacitor charges up to 2 volts. The capacitor charges up to 2 volts. If we're going to maintain Kirchhoff's voltage law, the only way that can happen, the voltage across the resistor will now decrease to 8 volts. And this will eventually reach 6 volts. This would have to be 4 volts. This will reach 8 volts. This will be 2 volts. Eventually, this capacitor will reach 10 volts, and at that time, when the capacitor reaches 10 volts, it's fully charged, the voltage across the resistor is 0 volts. So that's the first thing I want you to observe. Kirchhoff's voltage law applies here in this situation. Now, here's the interesting thing. All capacitors, whether natural or man-made, you're going to have a natural capacitor. All you need is 2 conductors and an insulator in between. For example, the ground and maybe a cloud. A cloud is a conductor. The earth is a conductor. The air between the two is an insulator, a dielectric. That's a natural capacitor. Or I can have a man-made capacitor. So all capacitors, whether natural or man-made, take 5 time constants to fully charge. 5 time constants to fully charge. So before, well, you actually have a graph I put on Blackboard. You may have looked at it, but let me put it right here. Let me draw this graph and explain a little bit about it. Then I want to go back to this circuit. So the graph looked like this. And if I had before, where I had a resistor value of 10 megohms, and I had a capacitor value of 1 microfarad, the time constant tau was 10 seconds. So what you could do is this. If this is time on this axis, and this is voltage, on this axis you'll have voltage or current. But here we're going to look at the voltage. Now we're going to look at voltage across the capacitor. Well, the capacitor can't go any higher than the source voltage. In this case, 10 volts. The capacitor can't go any higher than the source voltage. So this line right here represents the source voltage, and for that circuit, that would be 10 volts. The capacitor is going to charge up, and let me show you how it's going to charge, and I'll explain why it charges this way in a few minutes. So right here is t equals 0. That capacitor is going to charge up like this. Eventually, it's going to reach full charge, and it's going to stay at 10 volts. This is called steady state. Steady. Yeah.
What does that say at the bottom? T what?
T equals 0. T equals 0. Is it too dark, or can you? Did I just invite?
I can see it.
Can you see it? All right.
Yeah.
So look, the point I'm trying to make here is once that capacitor reaches full charge, which happens about right here, if I drop a line down, when it reaches full charge, all capacitors will completely charge up in 5 time constants. So if I know one time constant is 10 seconds, I divide this by 1, 2, 3, 4, 5. This would be 10 seconds. This would be 20 seconds, 30, 40. That capacitor will charge up completely in 50 seconds. That's what makes this so cool, because I have control over how quickly that capacitor charges up by choosing the proper value of RC for whatever time constant I want. And there are circuits out there that can respond to a voltage. Let's say when this thing gets fully charged, I can have something happen. So basically with a capacitor, I add the element of time to a circuit. Time. And again, I'll come back to that in a second. I just want you to kind of see how this works. I'm going to get rid of this, and we'll come back to the graph. Because what I want to look at now is this time t equals 0. T equals 0 the instant I close the switch. So let's go back to that. Let's go back to that. Now this is a critical point I want to make. So if it's not clear, please interrupt me and I'll go back, because I want you to see this idea of t equals 0. So I'm going to go back and open up the switch. I'm going to open up the switch. And we're going to assume there's no charge in the capacitor. So the capacitor is uncharged. Now the way the capacitor works, if you remember, our definition of voltage is charge as a separated charge, a separation of charge. And when I charge a capacitor, what happens is current flows into the capacitor and deposits charge on the plate of the capacitor. For every negative charge, every positive charge that appears here, you can think of it as negative charge appearing here. Now we know positive charge doesn't really move, but it's customary that just when you show this, you just think of positive charges flowing. So for every positive charge that appears here, negative charge appears here, and in between here you have a dielectric. So what you have is a separation of charge. You have a voltage across the capacitor. But at t equals 0, no charge is in the capacitor yet. So here's what that means. No charge is in the capacitor. If you take a voltmeter and put it across the capacitor, here's my voltmeter. I don't know if you can see that grid. So here's my voltmeter. I'm going to put it across the capacitor, and then I'm going to close the switch. When I close the switch, no charge is in the capacitor yet. And remember, charge equals voltage. If there's no charge in the capacitor, there's no voltage across it, but Kirchhoff's voltage law still applies. So that means the voltage across the resistor for this particular voltage source would be 10 volts. And the voltage across the capacitor is 0 volts. 0 volts. Let's think about what that means, 0 volts. Let's look at this in another circuit. Let's say I have a circuit, we'll just keep it simple here. I have two resistors in the circuit. I got R and R. Just to keep the math simple, we got two resistors, same value. And I'm going to hook it up to a battery. I'll just make it 10 volts. And I'm going to hook a voltmeter to the bottom resistor. Now, if these two resistors are the same, each resistor is going to get how many volts? I got 10 volt source, two equal resistors. What is the voltage drop across each resistor?
Is it 5?
It's 5 volts, right? Clearly it's 5 volts, but watch this. If I take my voltmeter and hook it across the bottom resistor, it's going to read 5 volts. While that's hooked up across that resistor and is reading 5 volts, I'm then going to take a wire and connect it from here to here. Now, after that quiz that you took home, that quiz with shorts and opens in it, you know that this is a short. If I short out that bottom resistor, the volts across the resistor now is going to read 0 volts. There's a couple ways to think about it. I have a short circuit, basically an ideal short is 0 ohms. I have 0 ohms in parallel with R. That's going to be 0. Or another way to think about it is current takes the path of least resistance, so current's going to come down through that first resistor and bypass the second resistor. If no current goes through the resistor, there can't be a voltage drop across it. Either way you think about it, this bottom resistor now, 0 volts. Top resistor has a whole 10 volts across it. This is the key idea that the voltage across a short circuit is 0 volts. The voltage across a short circuit is 0 volts. I just showed you that here. So if I'm telling you at T equals 0, all the voltages across the resistor, the capacitor has a voltage of 0. That means a voltage of 0 across the capacitor, a voltage of 0 across a short circuit. At T equals 0, a capacitor is equivalent to a short circuit. At T equals 0, a capacitor is equivalent to a short circuit. Now, does anybody want to ask me any questions about that? That is a key point. I'm going to give you another key point in a second, but I want to make sure this is crystal clear. Anybody have any questions over what I just did? At T equals 0, a capacitor is equivalent to a short. The reason I'm saying that, at T equals 0, voltage across the capacitor is 0. I just showed you that if you have a short circuit, the voltage across a short circuit is 0. That means that the two voltages are equal. That means that at T equals 0, a capacitor is behaving exactly like a short circuit. Therefore, I can say at T equals 0, a capacitor is equivalent to a short circuit, equivalent to a short. Any questions?
So if you hooked up an ammeter instead of a voltmeter at that across the capacitor, you would read current?
Are we looking at this circuit or this circuit? This circuit?
Yeah, this circuit. So if you had the short, yeah.
Yeah, so if I have, let me show you what, that's actually a good question. Now remember, if I hook up an ammeter, I can't put it across. An ammeter goes in series, but here's another way to think about that. At T equals 0, here's the circuit that you would see. At T equals 0, I'm going to redraw an equivalent circuit. I got my switch. I got my capacitor. When I close that, if I tell you that the time is 0, remember T equals 0, that's the essence I close the switch. If I say that, then the equivalent circuit is this. This capacitor is shorted out, and the equivalent circuit is just a piece of wire like that. And if I have an ammeter down here, the current I'm going to read in the circuit is going to be V over R. You see it?
Thank you.
Does everybody see what I mean now when I say at T equals 0, the capacitor is equivalent to a short? That's important, right? If you're writing this down, that's a key point. There's going to be 3 key points if I don't run out of time. There's going to be 3 key points I'm going to try to deliver to you today. That's point number 1. At T equals 0, the capacitor is equivalent to a short circuit, and I just proved that to you here with a little bit of logic. Any questions? Okay, let me go back to the graph. The graph looks like this. And this graph just kind of shows you how the capacitor charges up. So what I had was this graph. I had on this horizontal axis, we had time. And over here for right now, we have voltage. And I told you that the capacitor can only charge as high as the source voltage, which for this circuit was 10 volts. And then I showed you how the capacitor charges up. I didn't really talk about why the curve is as it is, but I'll get to that in just a second. So what I said was the capacitor is going to charge up like this, and eventually it's going to reach full charge. And when it's fully charged, then it'll stay constant. For this circuit, it'll stay constant at 10 volts. But right here, where it reaches full charge, that happens at 5 time constants. All capacitors charge up fully at 5 time constants. And what I just showed you here was at this time right here, this time, t equals 0, the capacitor is behaving as a short. Now, the reason this is so important is, probably not today, but next time I'm going to give you a problem. And that problem, I'll give you, it's the same circuit, but when you look at the circuit, determines how you solve the circuit. If I say, look, if that circuit has capacitors in it, and I say solve the circuit and t is equal to 0, all those capacitors in the circuit are shorts. And you got to remember that. You got to basically replace every capacitor with a short. So that's time number 1 I'm going to look at. T equals 0, or t sub 0, the capacitor is a short circuit. The other time I want to look at is this one though, 5 time constants. Here the capacitor is fully charged. It's fully charged. After 5 time constants, all capacitors are fully charged, no matter what the value. So I want to go back to this circuit and just using a little logic, let's look at what happens when it's fully charged. So let me clean it up a little bit, and then I'll show you what I'm saying. So I'm going to go back. We're going to assume that the capacitor has no charge on it initially. I'm going to open my switch back up. And now I'm going to close the switch. But before I close the switch, I'm going to hook my voltmeter up. Actually, let me think about this. No, I won't hook it up yet. Here's what I'll do. I'm going to close the switch without hooking the voltmeter up. We're going to hook the voltmeter up when that cap's fully charged. So watch what happens. Now notice I don't have a value for R and C. It doesn't matter what the value is. Any capacitor resistor combination is going to behave this way. The only thing the RC does, that combination of R and C, is change how quickly it behaves this way. But watch what happens here. Let's walk through it again. I close the switch. T equals 0. The capacitor is a short circuit, so the voltage across the capacitor is 0. And for this particular voltage source, the voltage across the resistor is 10 volts. And now we start going through those time constants. Current starts to flow into the capacitor. That capacitor starts to charge up. Let's say that capacitor charges up to 3 volts. If the capacitor charges up to 3 volts, remember Kirchhoff's voltage law always have to apply. So this voltage plus this voltage has got to equal this voltage. If this is 3, that's got to be 7. Eventually, this will come up to 5 volts. This will drop to 5 volts. This will charge to 9 volts. And eventually, 1 volt, this thing will be fully charged. This is 10 volts, which means the resistor voltage is now 0. At this point, no current can flow in the circuit. How can it? Look, you have a potential difference. You have a resistor. This is 10 volts, and over here you have a capacitor, also 10 volts across it, and these are series opposing. So no current can flow through the resistor because the voltage on this side of the resistor is 10. The voltage on this side of the resistor is 10. So the voltage drop is going to be 0. A resistor with no voltage drop across it, well, no current can flow through it. No current flows once it's fully charged. But look at this. Here's the interesting thing. Once it's fully charged, once that capacitor reaches steady state, once it reaches the 10 volts, I'm now going to take my voltmeter and hook it up. Now watch this carefully. I'm going to take my voltmeter and put it across the capacitor like this. And what would you expect the voltmeter to read? If I go across the capacitor, what will it read? Right now, what would it read? Let me rephrase. Go ahead. Say it again.
10 volts, right?
It's going to read 10 volts. It's not, it's not, this is no trick. I've charged the capacitor up to 10 volts. I charge the capacitor up to 10 volts. If I put my voltmeter across it, I'm going to read 10 volts because that's what's across the capacitor. So now this is reading 10 volts. But here's the thing I want you to get. Capacitor store charge. So if I wanted to, what I can do is I can take this capacitor out of the circuit. And I can move it somewhere else. I'll put it right here. And now I have 10 volts of charge in that capacitor. 10 volts of charge. I have 10 volts stored across that capacitor. If I want to use that 10 volts later, I can use it. That's the purpose of storing charge. You store anything because you want to use it later. But the question is this. If I take the capacitor out of the circuit, how does that affect the reading on my voltmeter? Now think about this. You know the answer to this. If I take the capacitor out of the circuit, so I got my 10 volts sitting right here across that capacitor, what reading will my voltmeter say? How will that affect the reading of my voltmeter and why? See if you can think about that.
Would it be 0?
Why do you think it's 0, Kevin? Why would you think it's 0?
Because all the volts is stored in the capacitor.
Do you guys remember experiment? Did you do experiment 7? That's the one you're supposed to do, I think, maybe you didn't do it yet. Where you had to open up the circuit at point B. Did we do that experiment before we?
Not yet.
We did do it. Anybody remember what happened? Remember you had the circuit? You had the circuit, and there was a resistor here, there was a resistor here, here, and here, and this was point B, and this was 15 volts. And they told you to open up the circuit at point B. And then you took your voltmeter and put it across here. Did we do that lab? Did we do that one?
Yeah.
Yeah,
What did you read across the open circuit? And we even looked at this. Remember when you Thevenized? It was the same exact thing when we Thevenized. When you Thevenized, exactly right. Somebody, I don't know who it was. Somebody said we read 15 volts. Why did we read 15 volts? It's simple, because we said that when you have a resistor with no current, if I open this up, no current can flow in the circuit. A resistor with no current going through it is equal to what?
A wire.
A piece of wire. So basically, this wire now is an extension of the positive terminal. You can replace that with wire. And all of these are just wire. So you're going to read if this is 15, this is 15, because the voltage drop across each resistor now is 0, they're equivalent to a wire. And again, when we Thevenize, remember when we Thevenize? When you Thevenize, let's say you had this, when we were Thevenizing, and we had a resistor right here, and maybe one right here, and my load was right here. And say this is R1, this is R2, and this was R3, and this was V. So when we Thevenize, you remove the load, and when I hook up my voltmeter, the voltage from A to B is going to be the same as the voltage across which resistor? This
R3.
R1, R3. Somebody said R3 correctly. Measuring from here to here is exactly like measuring right here. What happened to the voltage across this resistor?
No current.
0.
Exactly, no current. That means that resistor is a piece of wire. Well, that's exactly what we have right here. Look, if I take the capacitor out and put it up here, I now have an open circuit. No current can flow through the circuit, so that means this resistor has a voltage drop. It's just like this one. There is no voltage drop. So basically that resistor now becomes a piece of wire. So what will my voltmeter read?
10 volts.
10 volts. Now everybody, please look at this. That voltmeter is going to read 10 volts. If I take the capacitor and put it back in the circuit, now remember, the capacitor has 10 volts across its plates. If I put the capacitor back, now the voltmeter is reading the 10 volts across the capacitor. If I take the capacitor out, now the voltmeter is reading the 10 volts from the voltage source because there's no voltage drop across the resistor. What is that saying? It's saying that a capacitor that's fully charged is equivalent to what? An open circuit. A fully charged capacitor is equal to an open circuit. I just showed it to you.
So if you remove the capacitor, though, would it still have any voltage?
The capacitor is right here. Here's the capacitor. We charge it up to 10 volts. I take it out of the circuit and put it right there. So now I have charge in the capacitor. The capacitor looks like this. If you can see inside of it, there's positive charge here. There's negative charge here. So I got a separation of charge. That's a voltage. So that capacitor has 10 volts in it right now that you can use later on. So that's it. Now, if I take a voltmeter, look, if I take this voltmeter and move it up here, what would I read? What would I read up there?
10 volts.
10 volts.
But then there would still be 10 volts at the opening in the circuit also?
That's I think that's Mr. Payne. That's exactly what I'm trying to show here.
Okay.
There would be 10 volts here for the same reason. Let's say that these resistors are equal. So all these resistors are equal. And this is 100 volts. Well, if I open up the circuit here, this is going to get 50 volts, and this is going to get 50 volts. No, if I put my voltmeter from there to there, no current can flow that way. Remember, my voltmeter is not part of the circuit, so just ignore the fact that it's hooked up. I have an open circuit there. So I'm going to read here, whatever I read here, I'm going to read 50 because there's no voltage drop across that resistor. This situation right here is exactly what I have right here. If I open this up, no current can flow. And if there's no current flowing through that resistor, it looks like this. It looks like a short. So I'm going to read, I'm basically connected up across my battery. I'm going to read 10 volts across that open. You always read the total voltage across an open circuit in a circuit like this. Does that make sense to everybody? That is a very important key point. And I'm trying to show you why. If you can't follow this, you can rewatch this video. There's going to be a lot of dead spots in it because I went away from the camera a couple times, but I don't think I know how to edit that out. But this is critical. Here's what I'm trying to drive home to you. At t equals 0, a capacitor is equivalent to what?
Open
Short.
At t equals 0, a capacitor is equivalent to a short. When the capacitor is fully charged, and that happens after 5 time constants, the capacitor is equivalent to an open circuit. Now, I'm trying to show you that equivalency right here. So if you don't get it, rewind the video when we put it up on YouTube. Rewind it. By the way, does anybody know, is there a way to take those dead spots out in YouTube? I don't know how to edit videos. Is there a way to edit the video on YouTube? Or any YouTubers out there? Anybody know about that? Nobody knows? Okay. I'll look it up. But anyway, the key point, let me write it down. And I'm going to show you why it's important here in just a second. What I said was, I tried to prove it. At t equals 0, the capacitor acts like a short circuit, and at t, now this is greater than or equal to, because I can use that because of my graph. The graph looks like this. And I have my steady state voltage there. The graph looks like this, where it charged up, and then it stayed steady. So right at this point is my 5 time constants. So that's the equal part. That's the equal. Or when it's greater than 5 time constant, it's going to stay at the same voltage. So I'm not going to use an equal sign here. I'm going to say at t greater than or equal to 5 time constants, the capacitor is going to act like an open circuit. Write this down. If you're taking notes, write this down. Now, I would really, 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 really love it if you understood the logic behind this. And again, if you didn't follow it, please, when I put it up on YouTube, or you can look at it on Blackboard, go back and rewatch the video and try to follow the logic for this one and for that one. But even if you don't follow the logic, what you want to remember is this. All you really need to know to work the problem is this right here. I just wanted to show you why this is the case. But sometimes you got to really think about this stuff to see what's going on. So write this down, and then I want to show you why this is important, how you would solve a problem where this would come up. So now I forgot to put this on Blackboard, so I'm going to put it on the board. And I'll scan this and put it on Blackboard a little later today. But copy this down. If you have pen and paper, copy this down. And we're going to apply this idea to a circuit. So copy this circuit down. And again, I'll put this up on Blackboard sometime today, or definitely by tomorrow, and you'll have this paper. But this is exactly what I'm going to put on the board. So here is a circuit. All right, so copy this down. This is 50 volts. All the resistors are 25. Oh, this is C3. This is C2. Again, notice I don't have any value on the capacitors. I don't know what the number of micro, but it doesn't matter because they're going to behave a certain way. So here's the circuit. And what I want to know is, I want to know the voltage across each resistor and the current through each resistor at T equals 0. So imagine, if you want to, that I have a switch right here. Imagine I have a switch right here, and I close that switch. Bam, I close the switch, and now I have this circuit. So if I tell you the time is T equals 0, what I want you to do is tell me or figure out the voltage across each resistor and the current through each resistor. I'm going to pause for a second. I'll be quiet to give you a chance to think about it, and then I want you to try to work it out. Give me the voltage across each resistor, the current through each resistor at T equals 0. See if you can think about it, and then I'll I'll tell you how to think about it the correct way. So go ahead and try to work it. So what do I need to do? You can keep working, but tell me what do I need to do to solve the circuit? What's the first step?
Set the caps to shorts.
Set the caps to shorts. If I say on exam 3, you'll have this, well, exam 3 or the final. On the exam, whenever that is, if I say T equals 0, that means you're gonna, in your mind right away, that means those capacitors are shorts. So right away, each capacitor turns into a short. And once you replace the capacitor with a short, then you gotta say to yourself, how does that short circuit affect the rest of the circuit? So at T equals 0, this is a short. This is a short. This is a short. And that's the circuit you do your analysis on. So I'll be quiet. You see if you can figure it out. And I want to have something to say about this in just a second. Now, guys, what you want to remember, and this is the reason why I gave that quiz on shorts. If I have a short circuit in parallel with anything, whatever's in parallel with is out of the circuit. A short circuit takes it out of the circuit, makes it go to 0, whatever it is. Whether it's a voltage source or resistor, if it's in parallel with the short, it's not in the circuit anymore. So let's look at what happens when I do this. At T equals 0, C2 becomes a short, but all that does is connect this wire to that wire. Nothing really spectacular there. C1 becomes a short circuit. Well, all that does is connect this wire to that wire. No big deal there. But when C3 becomes a short, it connects this wire to this wire. And if you look at this long enough, you will see that I have one big short circuit right here. There's a short right here. What effect will that short circuit have on everything to the right? What effect will that short have?
Gone.
It's all gone. So all
So
of these wires.
resistor is the only one in the circuit.
Say it again.
So resistor 1 would be the only one counted in the circuit.
Resistor 1, exactly right. Resistor 1 is the only one in the circuit. Everything over here is shorted out. And this is how you get into trouble on the exam. If you don't see that, you'll make it harder than what it is. The fact that this short is in parallel with everything, the only thing it's not in parallel with is R1. This circuit is equivalent to this. I have a battery that's 50 volts, and I got R1 that's 25 ohms. So the voltage across this resistor is 0. The current through this resistor is 0. The voltage across this resistor is 0. The current through this resistor is 0. The voltage across every resistor except for R1 is 0. And the current through every resistor except for R1 is 0 because they're all shorted out. And so the actual current that flows in the circuit, this current right here, is just 50 volts divided by the only resistor that's really in the circuit, which is R1, 25 ohms, at 2 amps flowing. And that 2 amps only flows through R1 because when it gets past R1, when that 2 amps comes over here, ain't none of it going over here. It's all going just like that. At T equals 0, this is the circuit that we have. Any questions over that? Okay, now, here's what I want to do. I want to do the same problem, but this time we're going to go from t equals 0 to the other end of the spectrum. Now t is equal to 5 tau. So if you're drawing this, redraw the circuit, and then this time solve it for 5 time constants. So I'm going to erase it, and you go ahead and do it the way you think you should do it. All right, I think this is right. All right, so go ahead and solve this at t equals 5 tau. See what you get.
Tresser, turn off your goddamn mic.
Oh, sorry, man.
So what happens here? Tell me what happens.
The caps are open circuits.
Okay, so Kevin says the caps are open circuit. So on the exam, what you got to do, if I say 5 tau or greater, you got to open up the caps. The question is, when you open up the cap, how does that affect the current through a resistor or the voltage across it? So let's think about it. If I open up C2, it's fully charged, so it behaves as an open. What's that going to do to the current through this end? There is none. So the current, each resistor on this side is 0. If there's no current through the resistor, there's no voltage across it. So the current through and voltage across every one of these resistors here is 0. It's like they're not there. Look right here though. C3, when I open that up, well, that really doesn't do anything. When I open that up, it only affects the circuit when the thing that we open is in series with the capacitor. So when I have a cross in parallel with it, opening the capacitor will not affect it. So this is like, it's gone. Look at C1. When I open that up, the current that will get to this resistor, because this behaves as an open, no current can get through it, so it's like the resistor's not there anymore. No current to it means no voltage drop across it. You might as well take it out of the circuit. This resistor's out of the circuit. This whole end of the circuit is not there. The equivalent circuit is this one. And so you can easily see that each resistor, all the ones I erased, the voltage drop was 0, the current was 0. But for this one, the two that remain, each resistor is going to get how many volts?
25.
25. I got equal resistors. They're in series. So this one's going to get 25 volts. This one's going to get 25 volts. So all the other voltages are 0. V1 and V3 are both 25. The current in the circuit is going to be 50 volts over 50 ohms. I got 1 amp flowing. So each resistor, R1 and R3, are going to get 1 amp. Now notice that at the same exact circuit, but it's just the time I look at it. At t equals 0, it looked totally different than this. I forget what the resistors that stay, but you got it in your notes. At t equals 0, we have 1 resistor left. I think it was R1. At t greater than or equal to 5 time constants, this is what the circuit looks like. 2 resistors. At t equals 0, the current was 2 amps. At 5 time constants or greater, there's 1 amp of current flowing in the circuit. So this is where I said your analysis, the way you approach the problem, depends on what time you look at the circuit. What time you look at the circuit, if it has capacitors in it, that time that you look at the circuit is very, very important, as you can see. So, anybody have any questions over this? Because you can kind of see what I'm going to do to you now. I'm going to give you a problem, and there's 3 times that I can tell you to look at the circuit. Let me put the graph back up. Let's talk about those 3 times. The graph for any capacitor, whether natural or man-made, is like this. I got my steady state voltage. So right now, this is V. This actually can be V or I. I'll get more into this next time. But I can have voltage or current in this axis. I actually put this graph that's on Blackboard. Then you'll notice there's some other data, some other curves on there. I won't have time to talk about it today, but on Monday, when we get back together, I'll go more into this graph, and I have a lot to say about it. But for now, you know the graph looks like this. And right here, if I say look at it at that time, T0, then that's a short circuit. You replace every capacitor in the circuit with a short. You do your analysis. The question then becomes, how do those short circuits affect the circuit? If I have a short in parallel with anything, that anything is not in the circuit anymore. Take it out and redraw the circuit down to an equivalent circuit. If I say look at it right here where it's fully charged, well, that's going to happen at 5 time constants or greater. And in this case, that capacitor is going to act like an open circuit. If I say do your analysis and the time is t equals 5 time constants or greater, you're going to take each capacitor and replace it with an open circuit. Take each capacitor out of the circuit. And if I have a capacitor that's in parallel with something, at 5 time constants, when I open it up, that's not going to affect anything. If I have a capacitor that's in series with something and I open it up, that's going to have an effect on the circuit. So please go back and rewatch this video and make sure you understand the significance and the difference between t equals 0 and t equal to or greater than 5 time constants. Because when you look at the circuit, your analysis is going to depend when you look at the circuit, what do you replace with a short or do you replace with an open? It depends on when you look at the circuit. So that's 2 of the 3 times. 2 of the 3 times. The first one was t equals 0. The capacitor behaves like a short. T equal to or greater than 5 time constants. The capacitor is an open circuit, equivalent to an open circuit. That's 2 of the times. You might think to yourself, okay, well then what's the 3rd time? Well, the third time is the time between P0 and T greater than or equal to 5 tau. The time in between here, things are changing in the circuit. Let me show you what happens to the current. Let's go back to my original RC circuit, because I don't have current in this graph. I want to show you what happens to the current, and then I'm probably going to run out of time. But this would be a good place for me to pick up next time. So let's go back to our circuit. Now, I want to look at two things. I want to look at the current, what happens to the current in the circuit, and also why does the curve look like this? It starts off with, if I look at the slope, remember the slope? If I look at the slope is really steep right there, and then the slope levels off and eventually goes to 0. If I look at the slope of the line, if I make a line here, so if I put a line through here, then my slope would be delta V over delta T, or volts per second. The slope of a line would be volts per second. And so the steeper the slope, the more volts per second. The more horizontal the slope, the fewer volts per second. If I'm right here, I'm changing at 0 volts per second. So you can see at T equals 0, my volts per second is the fastest, it's the steepest. So in other words, the capacitor is charging up really fast when I first close the switch. And then as it starts to charge up, this is a rate. The rate at which it charges slows down. It's going really slow as I approach 5 time constants and at 5 tau. I still got voltage, but the rate, the volts per second, is now 0. Why is that? Why does it behave this way? And it's pretty simple to think about. This is really kind of a simplified explanation, but here's one way to think about it. If I have an uncharged capacitor, and the way I'm going to charge it up is I'm going to send current through that capacitor. So initially, there's no charge in the capacitor. I'm going to charge it up by sending current into the capacitor. So imagine that current is flowing. Here's my current flowing. So my current is going like this. I'm drawing positive charge because we're thinking about conventional current flow. So when this charge gets onto the plate, here's the charge on the plate of the capacitor sitting there. Now, if you remember, like charges repel. So when this charge tries to get on the capacitor, it's got to fight a little bit because this one's going to repel it. Before I had any charge on the capacitor, there was nothing on the plate to repel it. That's why it charged real fast. But once I start to charge this, I got charge on here. So now when the next one tries to come on, it's going to feel repulsion from this one. But it gets on there. But now that third one's going to feel twice the repulsion. But it gets on there. But every time I add charge, it's harder for the next charge to get on the plate because like charges repel. And I'm putting more and more charge down there that can push against the charge I'm trying to add even harder. So you can see why in the beginning when there's no charge to oppose the flow, it charges real fast. But as I start to charge it up, it gets harder and harder and harder for charge to go into the capacitor. Eventually, I can't get any more charge in there to say it's fully charged. And that happens when the voltage across the capacitor equals my supply voltage in that RC circuit. Now, I don't know if you guys are familiar with air tanks. If you're a mechanic and you're familiar with air tanks, this is a perfect example. You know the portable air tanks that you have, you can take it to a pump, and you can put air in it, and watch the meter acts exactly like this. If I have an empty air tank, when I first hook it up to put air in it, the air goes in really, really fast. The gauge will read the pressure. It moves really, really fast. But the more air I put in it, the more back pressure I get. The needle's going to slow down to the point to where it's going to start to just really, really slow down. So I'm getting up this curve right here to the point to where the pressure from the compressor and the back pressure from the air tank equal each other. No more air can flow into the tank. If you never worked with an air tank before, you don't know what the hell I'm talking about. But if you have, that's exactly what's going on here. A capacitor acts just like an air tank. You're trying to put air in it. It works the same way, same exact way. So I think we only have a few minutes left, so I'm going to end it here. But here's what we're gonna do next time. I want to talk about the current. So I'm not gonna get to current today, but to show you what happens to the current. I'm gonna explain why it happens in the next video. So as the voltage increases, the current's gonna decrease. So I can have V and I right here. So this is current right here for now. That's current. So if you think about it, in my circuit, I had a switch, I had a resistor, and I had a capacitor, right? If I close this at T equals 0, that capacitor is equivalent to a short circuit. So here's the circuit I have. At T equals 0, that capacitor is equal to a short circuit. So if I calculate my current at T equals 0, my current's going to be I equals V over R. That's going to give you the max current. You get the max current at T equals 0. And then as the capacitor starts to charge up, and again, we'll look at why this is the case later. As the capacitor starts to charge up, here's what happens to the current. And then 5 time constants, that current will go all the way down to 0. That current is decreasing at the same rate that the capacitor is increasing. The capacitor voltage is increasing. So, here's the takeaway from this whole thing. At T equals 0, the capacitor is equivalent to a short circuit. If I'm doing analysis at T equals 0, I replace all capacitors with a short, and I look to see what effect have on the circuit, realizing that if I have a short circuit in parallel with anything, whatever's in parallel with, I got to take it out of the circuit. T greater than or equal to 5 time constants. Now that capacitor is going to be equivalent to an open circuit. I'm going to replace all capacitors in the circuit with an open circuit and see what effect the open has on my components. Again, if I don't have, if the capacitor is in series with anything, when I open it up, it's going to stop the current from flowing through it. If it's in parallel with the component, it's not going to affect it at all. So T equals 0 is the one time I wanted to look at. T greater than or equal to 5 time constants is the second time. The third time is the time between T0 and T5 tau. The time between those 2 points is called the transient time. Let me write that down. The transient time. Now the word transient means changing. Change or changing. Changing. So transient time, what that kind of gives you a hint is things are changing between T0 and T5 tau. The voltage across the capacitor is increasing. The current through the resistor is decreasing, and you don't know it yet. But the voltage across the resistor is also decreasing. You saw that from the circuit. So in the transient time, things are changing. So if I want to do an analysis at T equals 0, I replace all the capacitors with the short. If I want to do an analysis at T greater than or equal to 5 time constants, I replace all the capacitors with an open circuit. But what if I want to do an analysis between T0 and T5 tau? That's where this is a little bit more interesting. That's called a transient analysis. And when you have a situation like that, you got 2 choices. Either you can use this graph, which you have a copy of. This is called the universal time chart. You can either use this graph to do a transient analysis, or there's a set of equations I'll give you in the next video that you can use to solve the problem. So we'll look at transient analysis in the next video. Okay, and so there's some other handouts I have a chance to get to because I need to go through this stuff first. So just hold those off to the side on Monday, and we'll come back to it. We'll do a transient analysis and some other circuits I want to show you that have to do with these capacitors. Guys, I'm sorry about the lab too. I didn't give you a lab assignment. Actually, what I wanted you to do is already on Blackboard was experiment 6. So I didn't send a link out. You should already have the lab in your book. I know some of you don't have a lab manual. So I put the lab up. If you look at the link that says our last face-to-face lab, you'll see some labs I copied for people that don't have the lab manual. And so if you want to go ahead and do that in Multisim, you can. I believe it's lab experiment 6, I think it is. It's on Blackboard. You can check it out. But the reason I paused is I'm not really sure how I want you to turn it in. So you can bet, you can go ahead and do it. Do the next experiment. You can go ahead and do it. And I'll put this up on Blackboard, so you don't have to worry about it right now. But I'm not really sure how I'm going to collect that. So I will give you a link. I want to think about that a little more. So look for that over the weekend. I'll give you some information on the lab. I'll send that out. But if you want to go ahead and play around with multi-sim and that next lab, I believe is experiment 6. I'll check for sure, though, here soon. And then you can go ahead and start on that. Before I end this session, does anybody have any questions for me?
If you have multiple charging cycles, how reproducible is that curve?
Tell me what you mean by multiple charging cycle. Tell me what you mean. Because all
capacitor up like 5 times, would the curve look exactly the same on each of those after you've discharged it and charged it 5 times? Would it look exactly the same?
So are you saying that you charge it up and then you completely discharge it and then recharge it? Is that what you're saying?
Yes.
Yeah, so look exactly the same. As long as you don't change the value of RNC. Matter of fact, this works for any value capacitor. The only thing that changes is what you put down here. And that depends on your RC combination. But the shape of any capacitor, a really big capacitor like the one you see on the telephone poles, the really, really big capacitors, or the little tiny micro capacitors, all the curves look exactly like this. The only thing that changes are these numbers, because you get these numbers by taking the product of R and C. You have a really big R and a really big C, you will probably have seconds down here. More often than not, though, you'll have milliseconds or even microseconds. But it really depends on what you want to do. But you can see the beauty of this. The beauty of this is, now this is if you're electromechanical, you guys don't take electronics. But here's where the power of this comes in. There's a device, when you take electronics, you'll study it. It's called a comparator. A comparator, what it does is, it'll look for a certain voltage level, and when it gets to that level, it'll cause something to happen. So you can actually do this if you wanted to. Here's the neat part of this. But you need electronics to actually use it. You can actually take this circuit. Let's say you take a switch, and I got a resistor and a capacitor. All right. Since I have control over how fast this reaches, let's make this 100 volts. The symbol for a comparator looks like this. I'm going to draw it the wrong way, but you'll get it. So basically, a comparator is this device. I'm just going to do this for now. And it has this lead you hook to. I can hook this lead. I'll hook it right here. And what this is looking at is the voltage across the capacitor. And what I can do is I can have this thing to where when that capacitor comes up to a certain voltage, I can have this capacitor basically it'll output a voltage or current. Let's say I have a light bulb hooked here, and I got a 1 meg ohm. Let me change the color here. I got a 1 meg ohm. I got a 1 meg ohm resistor and a 10 microfarad. Well, the RC time constant would be R times C. It's going to be 1 meg ohm times 10 microfarads. That's going to give me that 10 seconds. So that means the graph looks like 1, 2, 3, 4, 5, 10 seconds, 20 seconds, 30 seconds, 50 seconds, 50 seconds. So I can actually close the switch and stand back, and 50 seconds later, I can get something to happen over here. This acts like a delay. Or depending on how I hook it up, I can hook it across the resistor and have the opposite effect. The point is, what this does to a circuit, it adds an element of time. So think of it like this, and this is a really bad example for me to give. I don't even know if I want to say it, since this is going on YouTube. But I won't even say it. I'm going to talk about bombs, but this is not a very good scenario to use, I guess, example to use. But we'll just say a circuit. If I have a push button here, if all I had before was resistors here, I push the button and whatever happens right away. But now, since I add the element of time, when I close the switch or push the button, I can actually have something happen in the future. When this thing counts up to a certain value, I can have this react, turn on the light bulb, open the door, whatever you wanted to do. I add the element of time to the circuit, and that turns out to be really, really, really powerful. We can do a whole bunch with this. So right now, we're not really looking at the applications of this. We're only looking at how it behaves. But once we look at the behavior, we can talk about some applications of this. And I think you'll see that this is pretty handy stuff here. So yeah, that's a good question. Anybody else have any more questions before I sign off?
So when's like the due date for the take-home quiz?
The one with the shorts in it?
I think so, yeah. The take-home quiz.
I hear an echo. I don't know why. Let me turn. Is that my audio? Okay, so there's two things. You got the exam. The exam I think is due on the 15th. There was if you're referring to the quiz with the short circuits in it, that might have already expired. I don't remember what I had it set to. But if you didn't turn it in, just send me a text. I think I have a link up there where you're supposed to upload it already on Blackboard. You can look and see, but if it expired, you can still turn it in. Just go ahead and work on it. When you get it done, send me a text, and I'll probably have your email to tell me if the link has already expired. And that'll take a real long time because you guys are turning in exam 2. You're turning that in, but you're really already ready for exam 3. Exam 3 is going to have more Thevenin on it. It's going to be more Thevenin. I'm going to give you we've already went through all this, so you should be ready for it. There'll be another Thevenin maximum power transfer problem. I'm going to give you a problem on mesh analysis, nodal analysis, and superposition, and a couple other things. I just don't want to overburden you with exams. I gave you a lot of time on this exam 2, but probably even before you turn exam 2 in, I'm going to put out that other exam. So, get that. If you got the quiz, go ahead and get that out the way. I want you to be focusing on these exams. That's going to be coming at you. Anybody else have any more questions for me?
Yeah, I have one question.
Okay.
You know the capacitor homework thing?
Yeah.
Can we go over figure 15-7? Because I was a little confused about what the dot means. Does that mean like it's separated out in parallel, or?
Wait a minute. Let me find it. Let me find it. I'm looking at it. That's a series circuit. Was that the one you're looking at?
Yeah, but that dot in between the C2 and C3, is that still going to be treated as parallel because it's opposite as it's in series?
They're not parallel.
Parallel?
Those are all in series.
Repeat that.
I said that circuit. That's exactly like figure 15. So, do you guys hear that echo? Are you guys hearing that? Let me stop.
Yeah, I think it's the system. It's still frozen for a while. On mine, at least.
Wait a minute, hold on.
The